everyone, this is Ashley Bedford, founder of the Runtime Diaries. Today we are on day 23 of our hashtag 30 Days of Code Challenge with Educative. Today's problem is called maximum running time of in computers. Let's get into it.
Today's problem is one of those rare algorithmic gems where the trick isn't about clever data structures. It's about reframing the entire problem. The challenge is called Maximum Running Time of in Computers, and it's all about batteries, computers, and squeezing out the absolute maximum running time from a shared energy pool. If you ever looked at a problem and thought, should I simulate this? Today's lesson will teach you, no, you should model it. So let's dive in. Here's what LeetCode gives us. You have in computers and they all need to run at the same time. You have a list of batteries, each with some capacity. And here's the good news. You can hot swap batteries between computers whenever you want. The goal is simple. Find the maximum possible number t such that all in computers can run for t minutes simultaneously. And the moment you hear the phrase maximum possible t, you should already be thinking binary search on the answer. But we're not there yet. This problem becomes dramatically easier if you see the real structure behind it. This is not about in individual computers. This is not about matching specific batteries to specific machines. This is about one giant pool of total energy. Add up all battery capacities. That's the entire supply of minutes you have. And if all in computers run for t minutes, you will need in times t total minutes of energy. This gives us a natural upper bound. T is at most the sum of all batteries divided by n. You can't squeeze more time out than the total energy allows. At first glance, many people try something like this. Assign batteries to machines, track which ones run out, switch batteries, track partial usage, swap again, repeat. It gets complicated instantly. But remember, we can swap batteries freely. The order doesn't matter. The exact pairing doesn't matter. Which battery goes to which computer does not matter. All of that detail collapses into one single question. Can we support t minutes of runtime across all in computers? And that means we can reason in terms of aggregate energy instead of individual assignments. Let's say we want to test if a certain time t is possible. Each battery contributes up to t minutes, not more. So we take each battery and we cap it. The contribution is the minimum of the battery capacity and t. Then we sum all contributions. Total equals the sum of min of battery and t for all batteries. If this total is at least n times t, then running all computers for t minutes is possible. If not, it's impossible. Why do we cap each battery at t minutes? Because no single computer can use more than t minutes from one battery. After t minutes, every computer is done. Any battery with more than t minutes contributes exactly t, since extra energy can't be used in this scenario. Batteries with less than t contribute everything they have. It perfectly mirrors reality without needing to simulate any swaps. And this is exactly why the greedy simulation approach fails. Trying to distribute batteries in the best order becomes a nightmare. You try to pick the largest for the weakest, or combine partial drains, or track how many minutes remain on each battery. And you still wouldn't cover all edge cases. None of that is needed. Once you switch to aggregate energy, the entire problem collapses into something clean and efficient. So now that we can test whether a given t is feasible, and we know feasibility changes monotonically, what does that mean? If t equals 5 is possible, and t equals 6 is possible, but t equals 7 is not possible, then all feasible values of t form a solid range. That is exactly what binary search is built for. Binary search on the answer is one of the most powerful patterns you can build into your toolkit. Here's the binary search approach. First, we know left equals 0 minutes is always possible. Second, the upper bound is right equals the sum of all batteries divided by n, using integer division. Third, while left is less than or equal to right, we compute mid as the average of left and right. We check if we can run for mid minutes. If yes, we move left up to try to run longer. If no, we move right down because mid was too ambitious. At the end, right will be the largest feasible t. This is clean, predictable, and it scales beautifully. And here's the feasibility check in code form. We define a function called canRun that takes t as input. We initialize total to 0. For each battery in the batteries list, we add the minimum of battery and t to total. Then we return true if total is at least n times t and false otherwise. Capping each battery at t minutes ensures we never overestimate the available energy. Compare total to n times t, and that's it. Putting it all together, here's the complete solution. We calculate total underscore energy as the sum of all batteries. We set right to total underscore energy divided by n using integer division and left to 0. Then we enter a while loop that runs as long as left is less than or equal to right. Inside the loop, we compute mid as the average of left and right using integer division. We initialize total to 0. For each battery in batteries, if the battery is less than mid, we add the battery value to total. Otherwise, we add mid to total. If total is at least n times mid, we move left to mid plus 1. Otherwise, we move right to mid minus 1. After the loop exits, we return right. This is an elegant, deterministic, and optimal approach. Let's break down the complexity. Binary search performs about log of the sum of batteries divided by n checks. Each check loops over all m batteries. So the total time complexity is O of m log m, where m is the maximum possible running time. The space complexity here is just a few integers, so it's O of 1.
Let's walk through a concrete example to solidify the intuition. Batteries equals, from left to right in the array, 10, 10, 3, 5, and n equals 3. Total energy equals 28. Upper bound equals 28 divided by 3 using integer division, which is 9. Now, binary search explores different values of t. The first iteration, we try t equals 4. We calculate the total available energy as min of 10 and 4 plus min of 10 and 4 plus min of 3 and 4 plus min of 5 and 4, which equals 4 plus 4 plus 3 plus 4, which is 15. We need 3 times 4, which is 12. Since 15 is greater than or equal to 12, t equals 4 is feasible.
We move left up to 5. Second iteration, we try t equals 7. Total available is 7 plus 7 plus 3 plus 5, which equals 22. We need 3 times 7, which is 21. Since 22 is greater than or equal to 21, t equals 7 is feasible. We move left up to 8. The third iteration, we try t equals 8. Total available is 8 plus 8 plus 3 plus 5, which equals 24. We need 3 times 8, which is 24. Since 24 is greater than or equal to 24, t equals 8 is feasible. We move left up to 9. The fourth iteration, we try t equals 9. Total available is 9 plus 9 plus 3 plus 5, which equals 26. We need 3 times 9, which is 27. Since 26 is less than 27, t equals 9 is not feasible. We move right down to 8. Now, left is 9 and right is 8. So left is greater than right and we stop. The final answer is t equals 8. This means that with flexible battery swaps, the total energy is distributed such that every computer can run for 8 solid minutes. The 2 large batteries of 10 each contribute 8 minutes apiece, and the smaller batteries of 3 and 5 together contribute the remaining 8 minutes for the third computer. Here are the most common mistakes people run into. First, using battery instead of min of battery and t. This overestimates the available energy. Second, using floats, which cause rounding issues, so always use integer division. Third, reversing your binary search boundaries. Make sure you move left up when the answer is feasible and right down when it's not. Fourth, thinking you need to assign specific batteries to computers. You don't. Think in terms of aggregate energy. And fifth, overcomplicating it with greedy simulation. The aggregate energy model handles everything. Once you understand the aggregate energy model, all of these pitfalls vanish. If you take nothing else away from this video, take this. First, think in terms of shared resources, not individual assignments. Second, cap contributions with min of battery and t to avoid overestimating. Third, feasibility is monotonic, so binary search works perfectly. Fourth, the upper bound is total energy divided by n. And fifth, binary search on answer is a core algorithmic pattern. These binary search on feasibility problems appear everywhere in system design and algorithm work. Mastering them is a huge unlock.
And that's a wrap for day 23 of our hashtag 30 Days of Code Challenge with Educative. If you like this video, like it down below, share it with a friend, subscribe to our YouTube channel. We would love to have you for many more videos and LeetCode breakdowns. We'll see you again next time.